Or if you have an annoying kid that talks all the time, you can ignore them. Everybody else is like, I ignore them. So when we have a constant stimulus, those sensory receptors will adapt. They will not be as sensitive to it because it's picking it up all the time. Now, adaptation can be adjusted both consciously and subconsciously. So a lot of times we train children, we don't like to call it training like dogs, but essentially that's what you're doing, is you're training children to respond to certain catchphrases, right? I'm sure a lot of us either had this training or our kids had the training. When we say crisscross, what do we hear? Applesauce, right? And that usually has trained our children to sit down Indian style on the floor. I don't know if you can say Indian style or not, but anyway, cross-legged on the floor and be quiet because the teacher's about to talk to you, right? Or this could be on a test and magically you start paying more attention because this could be on a test. I don't use that phrase because I would be saying that all the time. You would adapt to, and this is on the test, and this is because it's all on the test. So sometimes we can consciously change that adaptation. Sometimes we do it without even thinking about it. It's kind of like if you've ever walked into a busy room with everybody doing conversations and you hear somebody say something that you find interesting. It's probably like a hobby you have, but you don't know that person, but you still eavesdrop on their every conversation because you know everything they're talking about. They're like, ooh, I want to tell you about that, but I can't because you're a stranger. Anybody else get those bad ears every now and then when you hear other people's conversations? You've just consciously adapted. Your hearing got a little bit better because they were talking about something you were interested in. So you weren't thinking, I'm going to eavesdrop on these people. But your brain was like, this is interesting. I want to know more about it. I'm going to pay more attention. So you can adapt to be a little bit more sensitive sometimes. Now, who adapts is going to give us whether if it's peripheral adaptation or central adaptation. So peripheral adaptation is when the peripheral nervous system adapts, and central adaptation is when the central nervous system adapts. So peripheral adaptation, sensory receptors subjected to unchanging stimulus, it's constantly become less responsive over time. The receptor is going to adapt. Example, thermoreceptors, right? We see this especially with little kids and when they go out to play in the snow and you can see them out there partially frozen with little snot sickles. And like, it's not cold out here. I feel fine. It's like, you're frozen, dear. Come in. Defrost. They don't feel cold anymore because they're used to it. They've been out there the entire time. The rest of us, when you first walk into a room, it's like, oh, it's cold in here. But we get used to it. You do this in the lab room every day. It's like, it's cold, and then we get used to it. Central adaptation is where conscious awareness is going to disappear. So we still have the sensory neurons still sending input to the brain, but the thalamus is like, we don't need to know about this anymore. You need to shut up, okay? So we stop getting that information to the cerebrum, so we stop perceiving it, even though those sensations are still coming in. So this helps us to reduce certain stimulations like odors. We've all seen the Febreze commercials where you've gone nose blind to something. Nose blind is central adaptation, where you don't smell a smell that's being constant. So again, this is how cat people can be cat people and okay with it. They can't smell it anymore. And if you are a cat person, you're constantly worried that, are you that cat person? We also have cats and then they wonder, can they smell me? Okay. So maybe they can, maybe they can't. Depends on how adapted you are. Same thing happens again. Why people can live in Hereford, because that place does not smell pleasant. Okay? And it changes, right? Most of the time it's cow. I swear one day I went there to teach and it smelled like wet hair. I was like, what? Why does it smell like hair in this place? Hereford. Okay, so it's one of those, they adapt. It goes away. It's why you can cook dinner and you don't smell the dinner that you've cooked, but if you go outside and come back in, all of a sudden it's like, oh yeah, I burnt dinner. Okay, so we centrally adapt to it. We do the same thing with pain. So that pain sensation, if you wake up one morning and your back is sore because you lifted something heavy, that signal's coming up to the thalamus. Eventually the thalamus is like, all right, sit down and shut up. We don't need to hear about your whiny back anymore. And it blocks that pain sensation. So the pain goes away. And then later in the afternoon, when it's all quiet, you're sitting there nice and still, it comes back, right? So sometimes the pain goes and comes. It's always coming. It's just every now and then the thalamus is like, all right, enough. Block you. I don't need to hear it right now. So you can block pain sensations. This is one of the reasons why they don't let people who have been injured look at their injury, because if the thalamus doesn't realize we have that pain signal coming in, you're not going to feel the pain until you see it. And once you see it, your brain's like, dude, there's a hole there. And then it's like, oh, it does hurt. It's because the thalamus is like, all right, bring in the pain. We won't block it anymore. Okay, so conscious awareness of the sensation, that's going to be central adaptation. Now, one type of receptor that never, ever, 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 ever adapts are proprioceptors. So proprioceptors tell us where our body is. So you're never going to forget where your legs are. So when you're walking, you don't forget where they are and move them wrong. Or you don't try to walk across the room while you're still sitting. So your brain always knows who's contracting, who's relaxing, who's stretching. So we know where our body is at all times so we don't injure ourselves if we try to move. So when we look at how receptors adapt, we have two types. We have tonic receptors and phasic receptors. So tonic receptors, again, are always active, kind of like once you have your phone and it's on, you turn it on, you can hear the dial tone. Back in the day when they used to be hooked up to the wall and people worried about serial killers cutting the lines to your phone, right? Yeah, that's like the plot of every 70s or 80s horror movie. The phone is dead, we're all going to die. Because it didn't have a tone anymore. Okay, so as long as you're alive, these guys are going to be sending to the brain. So what they do is increase or decrease the action potentials based on the increase or decrease of the stimulus. So if that stimulus gets more, it's going to fire faster. If that stimulus is less, it's going to fire less. Now, these guys are slow to adapt because they're always on. The brain gets used to them talking. And it's like, oh, well, it's just that guy. But once we realize, oh, he's shouting at me, maybe something has changed, then the brain's going to pay attention to it a little bit better. So it's kind of like the old school dimmer switches that were the round ones that you had to turn and turn and turn and they fall off. You have to stick them back on and keep turning. It takes a long time to go from the dark setting to the light setting because it's always on. Example of tonic receptors, nociceptors. Nociceptors pick up the sense of pain. So that adage, the pain lets you know you're still alive, is actually true. If your pain receptors were not firing, that receptor would be dead. Okay, so they're always talking to the brain saying, owie, 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 owie. And when it actually does hurt, then they start yelling. They start having faster action potentials. So again, sometimes it takes a minute to realize something has hurt. Phasic receptors turn on and off, kind of like a phaser, right? Pew, pew, pew. They're off and then they turn on. So normally inactive until they get turned on and then they turn off. These guys are like normal light switches. When you turn them on, light instantly bright. Turn it off, instantly dark. Okay, so they're very fast adapting. So example, thermoreceptors, right? If you get up in the morning and it's really cold outside, you don't walk halfway to your car before you realize you need a coat. Okay, you know instantly when you step outside, oh, it's cold out here. Okay, nobody goes halfway somewhere goes, you know what, I think it might be chilly. So you're going to know instantly with those thermoreceptors.
Thermo,
temperature. So stimulus type, what are we picking up? So our first grouping are the mechanoreceptors. Mechanoreceptors are going to generate that nerve impulse when you touch them. So they have those mechanically regulated gates that we really didn't talk a whole lot about. We talked about the chemical and we talked about the voltage, but mechanical, you just touch them and they open and sodium is going to come in. So you can touch it, you can have pressure, you can have vibrations, you can have stretching. Now we have three categories of mechanoreceptors. So our first ones are tactile receptors, touchy-feelies. These should look vaguely familiar because we talked about a lot of these in the skin chapter because your skin picks up touchy-feely kind of stuff. So they should look familiar, and if they don't, shame on you. They should by next Thursday. I know, the F word is coming. Final. Like, worst F word ever. Okay. So we have our tactile receptors picking up touch and pressure and vibrations, and we have 6 different types of tactile receptors. So the first ones are free nerve endings. These are just dendrites sitting in the tissue. They don't have any special structures or anything like that. And they're going to be tonic. They're always on, always firing. And they're going to have large receptor fields, so they're not very sensitive. And they can deal with touch and pressure. Then we have our root hair plexus. So again, that's that cluster of nerves that's around the hair follicle, so they can pick up any direction that the hair is moving. Now, they're usually phasic. They're off until your hair moves, and then they get turned on, which is why you don't feel that one hair you missed when you shaved until the wind blows, and then it waves at you, and you're like, I feel it. Right? It's the reason why, like when you put your hair in a ponytail, it feels tight for a few moments, and then it kind of goes away, and then you take your ponytail down, and you get that headache as all of your hair drops. That's because all those hair follicles are going, I'm falling, and your brain's like, oh, too much. Okay? And it hurts because it's overstimulating, too much touchy with those hairs moving. Tactile disc, we saw our Merkel cells, again, in the stratum basale. So how they work, you have this disc-like structure on the receptor, and a cell sits on top of it. That's the Merkel cell. Now, these guys are tonic. They're always on. And when you press on the cell, it presses on the disc that causes it to fire faster. It's very similar to if you're sitting with your car engine on in park, and you hit the gas pedal, it revs your engine. So your car is always on, but if you want to make it make more noise, you press the gas pedal and it's going to rev. And you let go of the gas pedal, it stops revving, but you can still hear the engine rumbling. That's what these guys are like. They rev. Anytime you press on that pedal, it's going to fire faster. And you release that pedal, it's going to fire slower.
Can you give an example of the pedal? Like of how you can increase the...
Other than the gas pedal example? So on an actual Merkel cell, it just sits there. So whenever you push it, it makes it fire faster. So you can feel somebody touching you versus not touching you.
Okay.
So kind of like a buzzer. Push the buzzer, makes a noise.
So like anytime you brush up against something is...
If it presses the Merkel cell, yeah.
Okay.
So we've got a lot of those in our hands. That's why they're so sensitive to anything touching your hands.
Okay.
So they're always ready to send off information. So small fields, very, very sensitive, and of course giving us fine touch. Tactile corpuscles, again, corpuscles are corpuscular, they're bubble shaped. And the tactile corpuscles we talked about in the skin were the Meissner's corpuscles, so the little guys in the papillary layer. Now they're phasic, they turn off and on based on if you're touching them or not. And they're going to deal mostly with fine touch. They can deal with a little bit of pressure because there's just a little bit of difference between pressure and a touch. And they can also do texture because texture is a combination of touching and not touching. Okay? They're very similar to if you had those color plates when you were a kid. Usually you see them for girls and you get the different heads and the different torsos and the different skirts and you put them together and you rub them and you make new outfits. Back before we had iPhones with like TikTok. Okay? So whenever you do one of those kind of rubbing pictures, or if you rub and color a leaf on a piece of paper, everywhere the leaf touches, you get that darker line so you can have the outline of the leaf. That's essentially what's going on. Your skin, you have all these different tactile corpuscles, and your brain can interpret who's being touched, who's not being touched, and that's how we can pick up texture. When we touch something that's bumpy or something that's pokey or something that's rough or smooth or anything like that. We kind of combine multiple Meissner's corpuscles so we can generate a mental image of that texture within our brain. Lamellated corpuscles are example again in the skin were Presidian corpuscles, picking up pressure in the reticular layer, the subcutaneous layer. So these guys are phasic, they turn off and on, and they're going to deal with deeper pressures. We also have them with the viscera. So you can tell the difference between somebody touching your tummy, poking your tummy, punching your tummy, because different layers of those cells are firing off. I just barely touch might stimulate a Merkel cell, where if you press a little bit, you're going to stimulate that Meissner's corpuscle. And if you really press, you're going to stimulate the lamellated corpuscle. And if you punch somebody, you get the skin guys as well as the viscera going, oh, somebody touched me. Okay, so you have those different layers of touch and pressure that you can put together. Ruffini corpuscles are tonic. Now, Ruffini corpuscles look just like our Pisidian corpuscles. They function just like our Pisidian corpuscles. They're picking up pressure in the skin and the joints. The difference is Ruffini are going to be tonic, always on. Lamellated Pisidian are going to be phasic. They turn off and on. So same look, same job, same function. One is phasic, one is tonic. So that's the only difference between those two. Barioceptors is our second category of mechanoreceptors. Again, the word bario means pressure. You might have heard this if you listen to weather channels, like, oh, the barometric pressure is changing, so there's a thunderstorm coming in or something. So bario always means pressure. So these guys pick up pressure changes in the walls of blood vessels. So our brain can know if we have high blood pressure, low blood pressure. They're going to be in the urinary bladder, so you know if you need to go potty. They're going to be in your stomach, so you know if your stomach is full, that kind of scenario. And then our final category of mechanoreceptors are the proprioreceptors. So those ones that monitor body position. And again, they never adapt. So they are neither tonic nor phasic. because tonic and phasic describe how the cells adapt. So they can't be either one because they don't do any kind of adapting. And we've talked about these when we talked about our reflexes. We have the muscle spindles or the interfusal muscle fibers that detect the stretch of a muscle cell. So if the muscle's contracting or relaxed or stretched. We have the Golgi tendon organ that picks up the stretch in the tendons. So are we a stretched tendon or relaxed tendon? The Golgi tendon organs, again, similar in appearance to the Ruffini and the lamellated corpuscles. The difference is one is going to be phasic, one is going to be tonic, and our Golgi tendon organs are neither because they don't adapt. So the adaptation type is what makes the difference between those three different cells because they look the same and they have the same job, just different types or abilities to adapt. Now, these guys, of course, are coming from the joint capsules, they're coming from the muscles, they're coming from the tendons, and they're going to be picking up movement, pressures, tensions within those systems.
So proprioceptors are phasic?
Neither. They don't adapt. So
Okay.
they cannot be phasic or tonic because that describes adapting. They're
Okay.
always on. They never turn off.
Okay.
So here's just pictures of our little guys. So we have the free nerve endings with the dendrites just hanging out in the cells. We have that tactile disc. So again, you would have that disc-like structure the cell sits on. So if we that cell gets pressed on, it's going to press on that disc and it's going to fire faster. If we don't press on the cell, we don't press on the disc, so we fire slower. Our hair follicle that has the receptor wrapped around it. The tactile corpuscle for touchy-feelies. We don't care about crafts. Ruffini corpuscles, lamellated corpuscles, again, they do the same job except one is tonic, one is phasic. Our muscle spindle fibers and our Golgi, and of course these are proprioreceptors, so they are neither tonic nor phasic because they don't adapt. They're always communicating with the brain and they're never blocked from the brain. Other stimulus types, we got thermoreceptors. They pick up temperature, hence the word thermo. Now we are 3 to 4 times more sensitive to cold than hot. We have way more cold sensors than we do hot sensors. And that's because on this planet, you're more likely to freeze to death than spontaneously combust. So we need to protect us and be more sensitive to cold. In our phasic, they turn off and on. Our chemoreceptors pick up dissolved chemicals. So you have to dissolve the thing either in blood or in mucus or in spit. So again, these are going to pick up oxygen and carbon dioxide levels in our bloodstream so we can manage those. When we smell, we dissolve it in the mucus so we can pick it up. When we taste, we dissolve it in saliva so we can pick it up. Our nociceptors pick up pain. You can just think, oh, no, nociceptors. Okay? They're painful. These guys are tonic, always on, always firing. They just fire faster or slower based on activity. And we have 2 types of pain. We have fast pain and slow pain. So fast pain is fast. It travels along type A fibers, so big axons, myelinated, saltatory propagation, 300 miles an hour. So this is our prickling pain or stabbing pain. So you're not halfway across the room after you've stepped on a sticker before you realize you stepped on a sticker. You know instantly if you found that sticker in your carpet because that pain's going to be sent to your brain very quickly. Slow pain, these are type C fibers, so 2 miles an hour, tiny little neurons that are unmyelinated, so they have to do continuous propagation. This is a burning or aching pain. So this is like your muscle pain. So you go to the gym today and you exercise, you feel good, you go to bed, you wake up and you're like, oh, ouch, okay? That's the type C fibers. It took a while to get to your brain to tell you, oh, by the way, you overdid it yesterday at the gym. Surprise, okay? So unfortunately, because you don't feel these kind of pains instantly, there's a lot of mythology with the pain. You'll hear, exercising people like, oh, if you stretch after you exercise, it won't hurt so bad the next day. Or if you drink a lot of water, it won't hurt so bad. Or if you, sit in a hot tub or you get a massage, that will make sure the pain doesn't happen. I'm all about massages and hot tubs all the time if you can, but the pain's still coming. So it doesn't matter how much you stretch after you exercise or how much water you drink after you exercise, or if you get a massage after you exercise. Once the muscle hurts because of lactic acid buildup or even micro tears, it's going to send that slow pain signal. It just takes forever to get to your brain for processing. So you don't feel it until hours later or the next day because of how slow it is. It's just like once you put something in the mailbox, it's coming. It may take 2 weeks for the post office to deliver, but it's on its way. There's no way to stop it. And so those are your slow pains. Now, as an important reminder, overstimulation of any receptor. If the light is too bright, it hurts your eyes. If the sound is too loud, it hurts your ears. If you touch too hard, it hurts your skin. So anything can be painful if it's too much because it signals so quickly to the brain gets overwhelmed and it's like, ouch, it hurts too much. Yes, ma'am?
So I've always been told, like, if you work out and you're not sore, then say something's good workout, or you didn't really work out those muscles that year, does that just mean that you did too much?
So if it hurts the next day, you either had oxygen debt, so lactic acid buildup, or micro tears to the muscle. Lactic acid buildup does indicate that you did work a whole lot because you made a lot of lactic acid. It's not necessarily a good thing because it's a lot of waste. Now, if it hurts because of micro tears, and that usually is pain that lasts for multiple days, that's too much because you don't want to tear something because tearing breaks things. So it depends on if it just mildly hurts the next day and it goes away really quickly, then it's just lactic acid buildup, not a big deal. It indicates that you worked a whole lot. But if you were breathing efficiently while you were working out, you're not going to hurt the next day. So it's not going to be a good indicator of, oh, it was a good workout, a bad workout. Because if you were breathing properly, you're not going to hurt no matter how hard you worked out.
You said, I don't know if you said this, but stretching releases the lactic acid from your muscle fibers. Is that correct? No.
Feels good though.
Okay.
I know. Stretching is still going to hurt the next day because they've already been signaled. I hurt. And they're like, oh yeah, don't stretch now. You've already been hurting. Okay, so, it just takes time and diffusion for the lactic acid to leave.
Mm-hmm.
Location of those receptors. This one's pretty straightforward, right? External receptors are on the outside. We'd all be doctors if everything was this easy. So they're going to get stuff from outside the body. So obviously touch and pressure and temperature and pain. Most of your special senses, sight and sound and so forth. Internal receptors come from inside of the body. So your viscera, your blood vessels. So this can be temperature, this can be stretching, this can be pain, this can be chemicals like oxygen levels and so forth. Now, once we pick up this sensation, once we have a receptor that picks up touch or picks up pain or whatever, now we have to get that information to the brain so the brain can process it. So we have a series of 3 neurons that get information from the receptors in the source, the skin or what have you, and get it to the brain for processing. And the nice thing is they're 1, 2, 3, so pretty much in order. Now, your first order neuron, this is the guy that is in the peripheral nervous system. This is an actual sensory neuron. So even though the second order neuron and third order neuron are carrying sensory information, they're in the brain and spinal cord. So they're not biologically sensory neurons. They are interneurons carrying sensory information. Okay, so it's a little weird, but again, they're interneurons. Only sensory neurons are the ones in the periphery. So first order are sensory neurons. They're going to carry the impulses to the brain and spinal cord. They're going to have their cell bodies in that dorsal root ganglia of the spinal nerve or the cranial ganglia, which is the same as dorsal root ganglia for a cranial nerve. So they're only going to have their axons go to the central nervous system. The second order neuron located in the spinal cord or the brain stem. These guys are interneurons because they're completely in the central nervous system. And they're going to receive the input from the first order neuron. And at some point they will cross over because we just learned that the left side of the body is going to be picked up and processed by the right side of the brain. So at some point we've got to cross over. And that crossing over is called decussion. That's the science way to say crossing over is decussion.
Decussion?
Decussion. Okay. So that way we can get it to where it needs to go in the brain for processing. Our third order neuron is located in the thalamus. So again, you can remember third order neuron, thalamus, third ventricle. They all start with THs, so they're all in that same little area. This third order neuron will get the input from the second order neuron and send it to the cerebrum so we can perceive the sensation. So it's the third order neuron that blocks. So when you go to sleep, the thalamus shuts down. All of the sensory information coming in stops at the third order and doesn't pass that point. Okay, so when you're asleep, your eyes are still sending information through the first order and the second order neuron, but since the thalamus is shut down, the third order don't receive, you don't become consciously aware of it. Okay, so this one lets you come into the conscious part, the cerebrum. Okay. So our spinal tracts, we talked about our spinal tracts on test 4, and now that we know a little bit more about the ordering and the neurons, we're going to talk about them again here. So of course, our spinal tracts are going to have the job of sending information from the peripheral nervous system up to the brain and spinal cord for the ascending tract, and of course the descending from the brain down to the body. So typically we can kind of guesstimate where they begin, where they end by looking at their name. So if we had a spinocerebellar tract, it begins in the spinal cord, goes to the cerebellum, so we know it's going up to the brain, so we automatically know that it's a sensory tract because we're going up to the brain for processing. Now, since we've gone over the different parts of the brain and we know the functions of the parts of the brain, what is the function of the cerebellum? Balance and equilibrium. So what do you think the purpose of the spinocerebellar tract is?
Balance and equilibrium.
Balance and equilibrium. This is where all those proprioceptors from your body are going to tell your cerebellum who's contracted, who's relaxed, who's stretched. So the cerebellum knows exactly where your body is so it can balance properly. So if we had damage to the spinocerebellar tract, the patient would lose all balance of their body. They would be able to move, they would be able to walk, but they wouldn't be able to not injure themselves. They'd bump into walls, they'd fall a whole lot. So they would have those concerns. So our first group are the anterior lateral pathways found on the anterior side and the lateral side of the spinal cord. So these were the red and orange guys I was trying to show you in the cross section on the little dude. So our first order neuron comes in and will synapse onto the second order neuron in the posterior gray horn. Then it's going to travel up to the thalamus and synapse onto the third order neurons. So we come in, cross over immediately, and then travel up the opposite side. So if it's your left toes you're feeling, we come in through the sacral region of the spinal cord, have decussion at that point across the commissure for the sacral region, and travel all the way up the right side to be processed on the right side. So we cross over very early on. So we have our lateral spinal thalamic tract. This one picks up pain and temperature, so you can know if you stepped on a tack with your foot or something like that. Anterior spinal thalamic tract, crude touch and pressure. We learned this on our last test as the ventral spinal thalamic tract, because again, anterior and ventral are interchangeable. So ventral vague, so basic stuff like this is hard, this is soft, this is, fluffy. We couldn't tell the differences or anything like that for this guy. So here's showing them. So here we have the first order neurons are red. That's the sensory neurons. The second order neurons are white. The third order neurons are black. Both of those guys are interneurons. So here we can see our lateral spinal thalamic. So the first order comes in, synapses onto the second order in the posterior gray horn, crosses over through the gray commissure to the other side of the spinal cord and travels up the lateral white columns, and then synapses on the third order neurons so we can pick up our body. Our anterior spinal thalamic tract, same pathway, but they're on the anterior side of the spinal cord instead of the lateral. So our first order comes in, synapses on the posterior gray horn, crosses in the gray commissure, travels up the white column, and then synapses on the third order neuron so we can feel our body that way. Okay, so if we had damage to the gray horn in the sacral region, we would lose all of these tracts. So you wouldn't be able to feel pain in that body part, or you wouldn't be able to feel temperature in that body part, or vague awareness in that body part if we damage the gray commissure. And this is one of the ways, again, they can pinpoint if you have spinal cord damage, where is it at? They go through all these different testings. It's like they can feel me touching their toe, but they can't feel temperature on their toe. That means they damaged their lateral cortical or their lateral spinal thalamic tract. That means we need to look around the gray commissure and the lateral white column, and they can see if the damage is along that route. Okay, so they can see if it's a spinal cord injury. And of course, they know the target I'm touching my toes, it's going to be in this part of the cerebrum. They can, if the spinal tract is okay, they look in that part of the brain to see if the damage is located there. Okay, so it helps us to track down where damage might be located by doing these different tract testings. The spinocerebellar pathway, again, is going to come from the spinal cord up to the cerebellum, dealing with muscle tone, dealing with posture. Now, these guys go to the cerebellum. They do not go to the cerebrum. And since they do not go to the cerebrum, they don't pass through the thalamus. So there's no third order neurons. We just have first and second. And of course, since we don't have third order neurons, we are not consciously aware of these. So these tracts are always sending up to the brain, again, because they're proprioceptors. We never turn them off, but we're not consciously aware of them because that's not its target. Its target's the cerebellum. So they don't even go to where we can tap into it consciously. And we have two tracts. We have the posterior spinocerebellar tract. These guys do not cross over. So if it's coming from your left foot, it comes into the spinal cord. It's going to travel up the left side of the spinal cord and be processed by the left cerebellar path. If we're the anterior spinocerebellar, we do cross over. So we come in on the left foot, we hit the spinal cord crossing over to the right side, travel up the right side of the spinal cord, and are processed at the right cerebellar hemisphere. So why do you think we need some of that information to cross over, but some of that information needs to go straight up? If you're the cerebellum, why would you need information from the posterior tract on the same side and the anterior tract on the opposite side?
To keep things, or is it like the word I'm looking for? So when you're trying to walk, one leg knows that one's taking a step and the other needs to know to pick up to keep things in sync.
Yeah, right. To balance, you have to know what both sides are doing, right?
Mm-hmm.
You can't balance on just one side. Both sides have to work. So again, when you lift up one leg, you have to know this leg is up, but the other side, we have to know that it's contracting so we don't fall over. So we have to have a complete body picture to both sides of the cerebellum so we can control the body properly, so we can have good balance and equilibrium. Because you can't balance if you don't know what both sides are doing.
So synchronization for that one?
Yeah, so we can have accurate information so we can balance.
Okay.
So they're showing you our spinocerebellar tract. So here we have the posterior guys coming in on this side and synapsing on the posterior gray horn. No crossing over, just traveling straight up to the cerebellum. Where we have the anterior spinocerebellar coming in, synapsing on the posterior gray horn, crossing over at the commissure, and then traveling up. Okay, so some cross, some do not. So we can get that complete picture of what the body is doing. And then our posterior column pathway or dorsal white column pathway. So they're found in the dorsal column versus the lateral or the anterior. So our first order neuron comes into the central nervous system through the dorsal roots of the spinal nerves or the sensory roots of cranial nerves. So depending on what we're picking up, that second order neuron will ascend and then cross over in the brainstem. So we're not going to cross over until we're completely protected by the skull. So as we try to show you on the anatomage guide, that blue line crossed over at the skull where the rest of them crossed over at the sacrum as they were coming in. So then after crossing over, we will synapse onto the third order neurons. This is going to give us detailed stuff. Okay, so fine touch and pressure, 2-point discrimination, body position, all that kind of fun stuff. So detailed information instead of vague information. And as I mentioned, we take two routes for safety purposes. So if we had damage to a gray commissure, we lose the anterior and the lateral pathways, but we don't lose the dorsal pathways because they don't cross in the spinal cord. They cross in the brain. So it doesn't matter what kind of commissure damage you have in the spinal cord, posterior is still going to get to where it needs to go. So this is why you can have a patient who can't feel pain, can't feel temperature, but they can still feel their foot. You know, how can you feel your foot and not feel temperature in your foot? Two different pathways. So that's going to tell the doctor, it's like, okay, I have a patient, they can feel their foot, I'm tickling them and they feel it, but I stabbed them and they don't feel the pain, or I put a cold piece of ice on them and they didn't feel that. That's got to be the lateral pathway that's problematic, not the dorsal. So they know not to look in the brain because if the brain can feel something, the brain's okay. So now they'll start looking at the common shears to see where those problems are located. And so you can use that to help isolate where the problems might be if we have some kind of damage or injury. Now, our dorsal white column pathway is separated into two paths. We have the fasciculus gracilis and the fasciculus cutaneous. So the fasciculus gracilis is the inferior half of the spinal nerve, so basically below the diaphragm. So your feet and your hips and your belly button, those guys are going to travel along the fasciculus gracilis. The fasciculus cutaneous is the superior half, okay? So above the diaphragm, your arms and your ears and your armpits and stuff like that would be the fasciculus cutaneous. So that's the difference between those two tracts. One is coming from below the diaphragm, one is above the diaphragm. So here they are. We can see that first order neuron's coming in, and it's going straight up the white column. It's not hitting or synapsing on the posterior gray horn. It's not crossing over at any common shear. It's going to go all the way up, and it's going to synapse onto the second that is going to cross over in the medulla, because the skull is a safe place to cross over. It's very well protected. And then we're going to go up to the third order to synapse. So this is going to be our super important information. It's similar to if you were going to mail your taxes in, pretend that you're not using TurboTax and you're going to mail in your taxes old school way. Where do you drop off your taxes? Mm-hmm. You're like, we don't do that. It's technology. If you were going to mail your taxes, would you want to put them in your mailbox?
IRS office?
Yeah, you'd go directly to the source. So you'd either go to the post office, because if they lose it, it's their business, or you take it directly to that location. You don't put it in your mailbox because it can get lost so easily, right? It can get stuck, blow out, wet, whatever. Okay, you want to drop it off as close as you can to that destination so you don't lose that information. That's how these work. We're going to cross over at the very last moment so we don't run the risk of losing any information or damaging any of the information coming in. So this is the more important stuff. The lateral and the anterior spinal thalamics, that's like putting your bills in your mailbox. Yeah, whatever, go ahead, cancel me, okay? Gets there when it gets there, okay? And more likelihood of issues, more likelihood of damage in those common shears as we come through, or losing it at that synapse in the posterior gray horn. So that's getting sensory information to the brain for processing. Now we need to get motor information from the brain out to the body so we can control the body. So that's, again, the somatic nervous system, the SNS, or sometimes called the somatic motor system or motor division. Now, just like it takes 3 neurons to send information up to the brain, it takes 3 neurons to send information down to the body. So we have a series of 3 as well. The first 2 are interneurons because they're completely within the central nervous system. The last guy is your somatic motor neuron. It is a motor neuron functioning as a motor neuron. So again, even though upper motor neuron, lower motor neuron say motor neuron, they're still actually interneurons. They're interneurons that are conducting motor information, but they're not physically a motor neuron because no part of them leaves the spinal cord or the brain. Make sense? So they act like it, but they're really not. Right? So our upper motor neuron, again, is an interneuron. It's going to have its cell bodies high in the central nervous system, so most often in the cerebrum. So these would be those guys in the precentral gyrus that's going to control your body. So part of the pyramidal cells and so forth. Lower motor neurons, they're going to have their cell body lower in the central nervous system. So they might be in the brainstem, rubiospinal tract, reticular activating system. They might be in the spinal cord. And then, of course, the motor unit, that's the somatic motor neuron going to the skeletal muscles to control the skeletal muscles. So its cell body is in the brainstem or the anterior gray horn of the spinal cord. Its axon leaves as a part of that ventral root to go to the muscles. So our first tracks are the corticospinal pathways or pyramidal system. The terms are interchangeable. This is the only voluntary tract. Even though all these tracks are going to the skeletal muscles, this is the only one that you can consciously do anything about. All the other ones do all the background running, okay? All the how much muscle tone is your muscles going to have while it's awake kind of scenario. So these are the ones that we can tap into if you want to twiddle your thumbs or wiggle your toes or anything like that. Now we have 3 tracts within the pyramidal system. The first ones are the ones that come out as a part of your cranial nerves. These are called the corticobulbar tracts. They have a different name because at some point someone goes, okay, you call them corticospinal tract because they go from the cortex to the spinal cord. And they're like, yeah. What about the ones that don't go to the spinal cord and just come out of the cranial nerve? It's like, damn it, now we're going to change the name. Okay, so they don't touch the spinal cord, so we can't call them corticospinal. So they're going to have their upper motor neurons are going to have their cell bodies in that central gyrus, the somatic primary somatic motor cortex. They're going to synapse on lower motor neurons that will then work with cranial nerves, ocular motor 3, facial 7, glossopharyngeal 9, accessory 11, and hypoglossal 12. So we can move the muscles of our eye, ocular motor, so we can move our jaw, we can move our face, our neck, our pharynx, so you can swallow and stuff. The corticospinal tracts, they're going to have their lower motor neurons in the anterior gray horn, so they're going to be in the spinal cord, so corticospinal proper. And we have two tracts based on crossing over. So our first one is the lateral corticospinal tract. Lateral corticospinal tracts are going to cross over at the very top of the spinal cord right after the medulla. Some of them actually cross over in the medulla. They don't even wait to get to the spinal cord. It's kind of like if you have one of those people that can't wait until Christmas, so they open a couple of presents on Christmas Eve because they just can't wait anymore. We also have family members like that. My mom was that way. It's like a week before Christmas. She's like, so you want to know what you got? Like, sure. Should I act surprised on Christmas? So these guys can't wait. So some of them cross over at the base of the medulla or right after we leave the skull. Now, sometimes you'll see the term along the pyramids. Now, this is just a shorthand way of saying action potential is traveling down the lateral corticospinal tract. Or you say along the pyramids. Okay, a lot shorter. So 85% of the corticospinal tracts are lateral corticospinal tract. 85% are going to cross over very early on, which is why a broken neck can cause quadriplegic issues. Because if you break 85% of the muscle control in guys, you can't move. Okay, you'll be paralyzed because you've snapped the guys that cross over very early on. Now, the anterior corticospinal tract, they're going to cross over within the white commissures as we get to our drop-off location. So if they're going to go wiggle your toes, the anterior corticospinal tract would go all the way down on the left side, cross over the white commissure in the sacral region, synapse onto the anterior gray horn, and then out. So they're going to cross over lower down. And again, we're going to have these two different routes for safety reasons. If we damage the white commissure, you lose the anterior corticospinal tract, but the lateral cortico is still in play. So if you were to damage the lower part of your spinal cord and damage the white commissure, you would have muscle weakness in your lower limbs, but you wouldn't be completely paralyzed. Now, if you damage the lateral corticospinal tract, you're dead in the water because that's 85% of the control systems, so to speak. 85% of those neurons going out to the muscles are going to be part of the lateral corticospinal. So here we are in picture form. So we're leaving down from the cortex. We've got the corticobulbar tract doing a quick UE within the cranial nerves. And then we've got the lateral corticospinal crossing over at the medulla, traveling down through the white column, and then synapsing onto the anterior gray horn before they can go out. The anterior corticospinal goes straight down all the way to the last moment, then cross over, synapse, and go to where they need to go. So two different routes just to make sure everybody gets to where they need to go. Your body's all about backup systems. Okay. Now, your medial and lateral pathways found on the medial side, lateral side of the spinal cord, these guys are involuntary. They're working at the subconscious level. So none of them are going to start in the cerebrum because we don't have a way to tap into these. So our medial pathways, they're going to control gross movements of the trunk and proximal limbs to maintain balance and equilibrium. And gross meaning big movements, not you, it's disgusting. Okay, so how do you hold your abs when you're walking? How do you hold your shoulders? How do you hold your hips so you don't lean or anything like that? So core body for balance and equilibrium and such. So we have three tracts in the medial pathways. Our first one is the vestibulospinal tract, and we learned vestibulo means balance. So this is the main guy that gives us balance and equilibrium for these muscles. So they're going to tell the muscles to contract just enough, not too much or too little, which would cause us to fall over or lose balance. The tectospinal tract, they're going to start in the superior colliculus and the inferior colliculus. So again, the superior colliculus deals with visual reflexes. So if somebody throws a ball at your head and you duck, you just have to duck your head. You don't have to duck your whole body. The inferior colliculi deals with auditory reflexes. So again, leaning closer to quiet noises, leaning away from loud noises. So this tract ends in the neck because we're dealing with moving your head to get better auditory information, or moving your head to have better visual reflexes. So they're not going to have to travel through. When you duck for something throwing at your head, you don't usually squat all the way down, right? You just duck the top part. It doesn't need to go deeper than the neck area. So it kind of ends with the cervical and the brachial plexus. You usually don't have leg ducking when somebody's throwing something at your head. Now this one, for me, one of the ways that you can remember it, because tectospinal, to me it sounds like techno music, right? And when you have techno music, you have lights and music and glow sticks and a whole bunch of, because that's what all techno music really sounds like. If not, look it up, kids. Okay, so lights, sounds, raves, craziness, techno. So tectospinal tract deals with auditory and visual reflexes. So just like techno music deals with auditory and visual sensory information. And then our reticulospinal tract starts in the reticular activating system in the brainstem. And again, the reticular activating system turns our muscles on, gives us muscle tone. So if the reticular activating system shuts down or the reticular spinal tract shuts down, we have no muscle tone. That's when we would faint or just fall over because we would have no muscle tone. As long as these guys are up and going, we're going to have muscle tone. So we can roll over in the bed, or we can sleepwalk, or we can do normal walking, that kind of stuff. The lateral, it's going to control distal upper limb muscles only, so elbow to fingertips. That's going to be our rubiospinal tract. And again, the rubiospinal tract starts in the red nucleus of the midbrain, called red nucleus because of all the blood vessels there. So this is going to give us tone and posture involuntarily for the elbows to fingertips. Now for us, not as important as it is in cats and dogs. So why is it more important for cats and dogs for their rubiospinal tract to be functioning compared to you?
Say that again.
Why is this tract more important in other mammals like cats and dogs where it's not so important in us?
Let me see.
Yeah, other mammals walk on 4 legs. So if they can't hold their hands right, they're going to fall. Humans, our rubiospinal tract is actually losing its effectiveness. Scientists often think that in the next couple of 100 years, we won't even have a rubiospinal tract because it's so unimportant for us because we don't balance on our hands like cats and dogs and so forth. So if you're still taking A&P in a couple of 100 years, you won't have to learn the rubiospinal tract. If you're still taking A&P in a couple of 100 years, you should think about changing your career goals. It's not going to happen. Okay. Now, of course, it only extends into the cervical spinal cord because it's going to come out through the brachial plexus to control elbows to fingertips, which ends in the base of the cervical region. So it's not going to be anywhere lower because those don't control your elbows anywhere lower. Okay. Questions about our tracts? Looked a little familiar from last test time. Okay. So looking at the motor and sensory homunculus. Isn't that a fun word? Homunculus. So a sensory motor homunculus is the graphical representation of either the motor areas of the brain or the sensory areas of the brain. So saying sensory homunculus would be similar to saying the Mona Lisa instead of that chick that Da Vinci drew. So it's a title of a picture. So as we talked about before, when we have motor areas of the brain, there's a lot of neurons to mobile areas like your hands and your face. Very little neurons to your lower back or your butt because they're not as mobile. Sensory-wise, your hands and your face are very sensitive, so there's lots of neurons for those guys, where your back of your knees or your lower back, not as sensitive, so we have fewer neurons. What the homunculus does is it draws a picture to represent that. So you would have a picture with a huge head because it's very sensitive or very mobile, and a little bitty body because it's not as sensitive or not as mobile. So the motor homunculus shows areas of the primary somatic motor cortex and the muscles they control. The sensory homunculus shows the areas of the primary somatic sensory cortex and the areas of the body that they feel. And of course, it's disproportionate because areas that are very sensitive will be drawn big, areas that are not very sensitive will be drawn small. So here's our examples. We have our sensory homunculus and our motor homunculus. We can tell the sensory from the motor because the sensory has organs, because you can feel if your tummy hurts or if you got to go potty, stuff like that. And then just weird random genitalia. Oh, they just so much penis right there. I guess it could be worse. So this is our sensory. So this has a huge face because our face is very sensitive. Big hands, very sensitive. Little bitty bodies, not so sensitive. Feet are kind of sensitive. They're a little bit bigger. Our motor homunculus, we know it's the motor because we don't have the random genitalia and the organs here. So just the parts we can control skeletal muscle wise. So big area for the tongue, very mobile. Big face, very mobile. Big hands, very mobile. Itty bitty body, tiny head, not very mobile. Okay. So this is just a quick picture to kind of help guide, like if you were a surgeon and you saw that your patient had damage right here, you would expect that they would not be able to feel their lower lip. If they had damage right here, they wouldn't be able to feel their calves. Okay. If they had, they wouldn't be able to move their wrist around. They'd have wrist drop and paralysis with their wrist. So you can use this to represent those areas. So if I had damage to both the pre and the post central gyrus in this location, not only would I not be able to feel my eyes and my nose, I wouldn't be able to blink and be able to wiggle my nose. So you can use this as a way to show and demonstrate those areas without having to write it in all teeny tiny. I think the biggest weird thing about this picture is that the guy has tan lines. I don't know why it has tan lines. He's drawn on. It's like Kevin Costner in the 90s. Why does this dude have tan lines anymore? If you haven't been around, 90s movie, Kevin Costner, he drops his pants all the time. Crazy guy. Okay. And we've seen this before. So our previous guys that we were looking at those tracks, there's a homunculus. They just don't put a head there. Looks a little more disturbing, but that's where the tongue is moving. This is where the hands are moving. So it says motor homunculus. We saw it before with the sensory too. There's the sensory homunculus. So we can see that this arrow is going to go to the hands. Basal nuclei. So we've already talked about the basal nuclei, but we've learned more than we did, at the beginning of the week. We now know upper motor neuron and lower motor neuron. So we're going to apply those informations. So basal nuclei, still deep within the white matter of the cerebrum, still sometimes called the subcortical nuclei. These guys do not control lower motor neurons because lower motor neurons are in the brainstem. Lower motor neurons are in the spinal cord. They're too far away for them to control. What happens, the upper motor neurons coming from the cerebrum, those pyramidal cells, as they pass through the thalamic area, the basal nuclei release neurotransmitters. They're going to release dopamine. And as that upper motor neuron travels by, the dopamine released by the basal nuclei will prevent the upper motor neuron from releasing as much acetylcholine. So it slows down the activity of the upper motor neuron, thus making sure we don't overstimulate the muscle. If we have damage to the basal nuclei, it can't release dopamine. There's nobody to pump the brakes on the upper motor neurons. They're going to dump all their acetylcholine, which will overstimulate the lowers and overstimulate the somatic motor neurons, so we get the tremors and the twitching and so forth. So the basal nuclei will adjust the activity of the upper motor neurons, not the lower motor. By the time we're in the lower, we've gone too far to influence. So the axons can synapse in the thalamic neurons and sprinkle their dopamine as we pass through the thalamus, or in the reticular formation, because while we're conscious, we want to make sure we want to contract, but not over contract. So still important in starting, stopping, monitoring movement, like how much do your hands swing when you walk? Do they stop swinging when you stop walking? Do you big steps, little steps, stuff like that? So normally tracks leaving here have an inhibitory effect. That dopamine pumps the brakes on those upper motor neurons so we don't overstimulate the muscles. So if we don't have the dopamine release, we don't pump the brakes, we overcontract and we get the tremors and we get the rigidity that we see with Parkinson's disease or Huntington's disease. Okay, just adding more detail to what we already learned. Still basal nuclei hanging out right there. Big bad hairy question about the SNS. All right, moving on to the autonomic nervous system. Are you all excited? It's the last chapter on this test. Woo! Last chapter of A&P 1. Okay, just trying to get you excited. Need more caffeine. So, comparing the somatic nervous system that we just got done talking about to the autonomic nervous system. So the somatic motor division lacks ganglia, right? All of their cell bodies are in the anterior horns of the spinal cord or the brainstem. Only their axons leave. With the autonomic nervous system, we do have ganglia. We do have neurons completely outside of the central nervous system. So we'll see ganglia within the autonomic nervous system. Our somatic motor neurons release acetylcholine. We've talked about that on test 3. And that's acetylcholine, again, stimulates skeletal muscle for contraction. So we're always going to have excitation in response to that acetylcholine. So the skeletal muscles will always contract in response to acetylcholine. With the autonomic nervous system, the postganglionic autonomic fibers, we're going to define that in a minute. I know big words, but we'll get there. They can release 2 different types of neurotransmitters. We can release norepinephrine, which is most of your sympathetic fibers, or we can release acetylcholine, which is most of your sympathetic. And the results can be inhibitory or excitatory. So we have 2 options with neurotransmitters and 2 options for the results. So you can get happy to see it or you can get depressed to see it. So we have options with the ANS that we don't have with the SNS. Now the adrenal medulla. The adrenal glands are little glands that sit on top of your kidneys. And a lot of our organs have a setup where we have a capsule on the outside, a cortex, and a medulla. Kind of like a peanut M&M has a thin candy coating, chocolate, and a peanut. Okay, so the adrenal medulla would be the peanut of the adrenal gland. The adrenal medulla makes secretions. It makes hormones that supplement the sympathetic division. The adrenal medulla makes epinephrine and norepinephrine. And again, epinephrine on the street is called adrenaline. Okay, and that's why it's called adrenaline, because it comes from the adrenal glands. Okay, that's how those hormones were originally named. And then they're like, oh, look at that, they're also neurotransmitters. So the hormones from the adrenal medulla can stimulate the neurons in the autonomic nervous system just like a neurotransmitter can. Now, the reason why these neurons can respond to a hormone just like you can respond to a neurotransmitter is because embryologically, back in the day, the adrenal medulla and the sympathetic ganglia, the nervous tissue and the hormone-producing tissue came from the same developing tissue. They grew up together. It's just like if you and your best friend grew up together and your best friend moved to Canada, you two still get the same jokes. And the Canadian's like, I don't get it, eh? Okay. So when you're raised with someone, you get the same jokes and you have the same, and they're like, what is wrong with you? I'm sorry, we were raised together. Okay. You still respond the same way. Same thing here. We can respond to hormones because they grew up together. So they can be influenced by those hormones, where the adrenaline isn't going to affect skeletal muscle, because skeletal muscle and the SNS didn't grow up with the adrenal medulla, didn't come from the same tissue. Okay. All of our autonomic motor pathways, again, consist of 2 motor neurons. That was our question on the board today, in a series. So you're going to have one coming from the brain and spinal cord, going to the ganglia, and then one going from the ganglia to the effector organs. And of course, the SNS just has the one. It has the somatic motor neuron with its cell body in the anterior great horn or the brainstem, and it's one axon going to the skeletal muscle. So this is one of the reasons, and we're going to get to the other, why skeletal muscles respond faster to commands than the heart or smooth muscle. We've got one guy telling us what to do instead of 2 guys. And anytime we put a middleman, it always takes longer to do something, right? So we'll get rid of the middleman so it'll be faster. So here are the guys in the picture form. So the somatic nervous system. So we have the one somatic motor neuron going to the skeletal muscle, where in the autonomic nervous system, we have 2 motor neurons. The first one goes from the central nervous system to the ganglia in the peripheral nervous system. And the second one is completely in the periphery, going to the target organs. And of course, different targets, skeletal muscle versus cardiac muscle, and smooth muscle and glands. Same thing, different author. So we can see the SNS, so the somatic motor neuron with its cell body in the anterior great horn. It has its axon lead as a part of the ventral root, myelinated, going to release just acetylcholine to the skeletal muscles where they will contract. Our autonomic, the first guy has their cell bodies in the lateral great horns because they're going to the organs. Lead is a part of the ventral root, myelinated, and it's going to release acetylcholine to the second guy, the postganglionic neuron, and that will go to the target and release either epinephrine or norepinephrine depending on our target. Big bad hairy questions? Pretty straightforward. So introduction to your autonomic nervous system. Class, autonomic nervous system class. Look, now you've been introduced. You're not strangers anymore. Okay. So the autonomic nervous system, again, goes to your smooth muscle, goes to your cardiac muscle, goes to your glands to regulate their activity. All of the involuntary stuff versus your skeletal muscle, which are your voluntary muscles. It is a motor subdivision of the peripheral nervous system. So again, the peripheral nervous system is separated into sensory and motor, and the motor is divided into the SNS and the ANS. So we learned that way back in the beginning of the nervous system chapter, and we saw the flow charts and such. Now, in order to operate, the autonomic nervous system has to have sensory input, right? You can't speed your heart up if you don't know how fast the heart is going. And why do you want to speed your heart up? Well, maybe because you don't have enough oxygen. Maybe because you're scared. So you have to have sensory input for you to tell your glands to produce more or less, or the heart to speed up or slow down, or the smooth muscles to contract or relax. So that sensory input is coming in from the autonomic sensory neurons, coming from the viscera, coming from the blood vessels. So structurally, the autonomic nervous system can include the autonomic sensory neurons, the integrating centers of this brain that processes that information to tell us what we need to do, and of course the autonomic motor neurons. Now, originally, the autonomic nervous system was called autonomic because it was thought to work autonomously, which is just a fun word. So autonomously means without outside control, okay? Works on its own. This is something that if you're into antique toys, back in the 1800s into the early 1900s, automatons were very popular toys. The most common automaton most of us probably know about is that freaking creepy monkey that has the bloodshot eyes and the symbols, and you wind him up and he just keeps symboling. And you're like, you're so freaking creepy. He's an automaton. He can work without you moving his body around. You just crank him and let him go. So automatons were toys that you could wind up, and they worked without strings. Okay. We also still use the word automaton if you go to theme parks, Disney, Six Flags, and there's some weird little Muppet that's moving around on a ride, or the little people from It's a Small World are singing at you, or the Pirates of the Caribbean are trying not to kill you, that kind of stuff. They're called automatons. They're robots. They don't use the word robot until recently. But automaton means that you can move without somebody moving you. You puppet without a string. So they used to think that the autonomic nervous system could work without the brain. You could cut your head off and the autonomic nervous system would just keep you going and going and going. That's not the case. They found out after using the guillotine for a few years that without a head, they're not going anywhere. Okay? You still have to have parts of the brain to control your autonomic nervous system. We have the hypothalamus. Again, it controls if you're thirsty, if you're hungry, what your water concentrations, when you go to sleep, hormones you release. We've got the brainstem, the medulla that controls heart rate and breathing rates and blood pressures, the pons that also influences those. So you can't survive indefinitely without at least the brainstem and the hypothalamus to keep you going. And of course, the hypothalamus and the brainstem we saw through the fornix receives input from the limbic system. So your emotional state can affect your autonomic nervous system. This is why you can get scared and your armpits start sweating and your heart starts racing, because that limbic system brought in that fear and your brain was like, run! And then it sent a signal to the medulla that said, speed up your heart rate so you can pump blood to your body so you can run away. And you can cool off the body by releasing sweat so you don't overheat as you run away. So we can influence the autonomic nervous system not consciously, but we can do it through the back door by the limbic system, because the limbic system, our emotions, can influence how the autonomic nervous system works. So again, limbic system found up the upper part of the brain stem, the hypothalamus region, mammillary body thalamus, fornix connecting it up to the prefrontal area of the cerebrum. So all those working together. So our autonomic sensory neurons, these are the guys that are sending in information about what the organs are doing so we can respond to that. So all of these neurons are interneurons because your organs are inside of your body. So they're going to be things like chemoreceptors that pick up if we have too little oxygen or too much CO2, so we can increase breathing, increase heart rate so we can deliver oxygen more efficiently. They can come from blood vessels so we can manage blood pressure if we need to speed it up, slow it down, that scenario. Organs, so we know if we need to empty our stomach or stop filling our bladder, all that kind of fun stuff. So they're going to transmit information concerned with pain, with pressure, with temperature, fatigue, hunger, thirst, all that, nausea, from the body to the brain for processing. Now, again, most of these things we're not consciously aware of. We're not perceiving them. They're just going to those lower parts so we can manage and manipulate our body. Now, if those signals get really strong, then we will become consciously aware of them. So if you went and ate at IHOP and got the E. coli from the IHOP, you were instantly sick. Now, you don't feel sick while you're eating your pancakes because it takes a little bit for the brain to realize you're sick. But as soon as that toxin entered the bloodstream, the medulla picked that up. It's like, oh, I don't feel good. And as it kept building and building, the medulla is finally like, we should tell the cerebrum because I'm about to hurl. And right before you vomit, your cerebrum's like, ooh, there it is. You did not feel the 2 or 3 hours of nauseousness leading up to that vomiting moment because your medulla is like, I don't need to tell you unless you need to do something. It's like, oh, time to do something. We're going to vomit. Okay. So whenever you're thirsty, your brain is constantly being told how much fluid you have, how much food you've had. And as soon as your stomach is empty, you're instantly hungry, but it's not to the point that you're consciously aware of it because it takes a while for it to get to the level that we need to clue somebody in. Just like when you do work at home, you don't always have to tell your boss what you're doing until it gets crazy, right? You can have really bad customers. You're not going to tell your boss about it until one of them starts trashing the store and you're like, oh, we should tell the boss about this crazy shit. Okay. But the normal weirdness in your customers, you don't tell your boss about because it's not a big deal yet. So it will be conscious awareness of this information once it gets big enough, once it gets important enough to be told. So our autonomic motor neurons, again, are going to regulate visceral activity either by increasing, exciting them, so speeding up your heart rate, speeding up sweating, or inhibiting or decreasing, slowing down heart rate, slowing down sweating. Unlike skeletal muscle, cardiac muscle and smooth muscle generally work even if neural impulses are interrupted. So again, your skeletal muscles are like, 2 or 3 year olds. You don't leave them home alone. You have to feed them. You have to clothe them. They can't do anything without you, right? Right. You just don't release your 3-year-old and be back in a week. Okay. That's your skeletal muscle. Have to have constant control. Your smooth muscle, your cardiac muscle would be like if you have a 16-year-old. No one goes, oh my gosh, I have to get home. My 16-year-old is home alone and might be hungry. No, your 16-year-old could probably use the air fryer or the microwave, or they can make some ramen noodles. They're fine. You just have to check in on them every now and then. When you wake them up in the morning to go to school, you don't have to tell them how to get dressed, but sometimes you do check right at the end to make sure they didn't do anything stupid, right? Depends on if you have boys or girls. With boys, it's usually just, it's 1 degree outside. Why are you wearing just a hoodie? They're like, it's fine. I'll wear gloves. You're like, I see your knees. What is wrong with you? It's cold outside, right? But they work on their own. You don't have to worry about them putting on their pants. That'd be really weird if you had to put on your 16-year-old kid's pants for them. Okay? That's how hard it is. The stomach. If we interrupt the neural transmission, they'll keep going for a little while. They just need to be checked on every now and then to make sure they don't go crazy. Now, your autonomic motor pathways, as mentioned, have 2 motor neurons in a series, one following the other. And we're just going to have to wait until next time. I know I'll give you something for Monday. So we should be able to finish up notes on Monday, and then we'll have Tuesday to review for the test 5 that opens Tuesday and closes Wednesday.
And then Thursday's our final.
Yep. Yeah, next week's Testapalooza. It's less terrifying if it sounds cool.
And when did you say the practical 4 closes?
So practical 4 is Monday.
Monday. Okay.
The pre-practical closes Sunday night.
Yes. Okay. Pre-practical closes.
Yes. We're earning our spring break. So practical 4 on Monday, test 5 on Tuesday, Wednesday, final on Thursday, sleeping and maybe on Friday, break off for a week, and then we come back, maybe, or not. Some of you won't be coming back. But you don't love me. Yes.
So what are we gonna be doing in terms